Go.
Okay, my name is Carl Littmann, and I actually regret that I can't stay for the whole conference because I will be missing a lot of great presentations and great people, but we'll go forward. My talk is basically about understanding nuclear fusion. For example, why four nucleons fuse together tightly to form a common helium nucleus. While we're kind of setting things up, I want to pass around a booklet that partly explains why even a single isolated nucleon, like a proton, holds its own self together, so to speak. Let me just do. Okay, thank you very much. Okay, so the first question is, why is there a so-called nuclear force that strongly holds many nucleons together in a nucleus? For example, there is a rare form of helium with 3 nucleons, that is 2 protons and 1 neutron. We might think that the 2 positively charged protons would repel each other, and thus the nucleus would fly apart and be unstable. But a mysterious nuclear force is credited with keeping the nucleus tightly together and stable anyway. I believe we can basically understand the origins of the mysterious nuclear force by studying the upper sketch in slide 1. That shows a flow in a wide cross-section of a pipe, and then through a transition, and then through a narrowed section of the pipe. We'll not repeat all the stuff in physics books, but basically the velocity of the flow in the narrow pipe region is much faster than in the wide region. That's so no traffic pileup occurs in the flow. My theories are also based upon various assumptions, and will only mention a few. The flowing fluid must be pretty incompressible, and the flow fairly smooth and not turbulent. Maybe it is either flowing, and maybe it curves around in a long circular-like path, and that may relate to Planck's constant, which is expressible also in angular momentum units, length times mass times tangential velocity. Anyway, when the pipe flow narrows, a lower pressure arises in the narrow region, maybe even a suction, in other words, a traction. And that pressure drop can be measured by a pair of vertical tubes shown in the sketch called a Venturi meter. And the pressure drop can also be expected by applying Bernoulli's equation for flow and energy conservation to the flow shown. We need not now repeat the math in physics books. The main point is this. The narrowing and the low pressure developed is not just limited to pipes. If we now look at the lower sketch, we note this. When those three nucleons touch, the opening near the center of their 3 nucleon pattern is very narrow. Even if only a modest amount of ether is flowing toward those 3 nucleons, that flow must begin to speed up if a goodly portion of it is to that small opening with regard to volume flow per second. I call that small opening the small donut hole or tunnel, and thus the nucleons are attracted to the relative suction near the narrowed center of their own pattern. That is, they attract. And I think that is the root cause of nuclear force, and that it is the basis of our interesting and diverse universe because it fuses various numbers of nucleons together, and that gives us common helium and so many other different atoms in this world. Now we'll try to go on to slide 2. One moment. When three nucleons fuse together, that few is enough to cause a substantial fusion energy release instead of just a little. And we note in the sketch oh, I see. This okay, well, we'll
I'll have no problem. You got it.
Okay. Okay. We note in the sketch a single prominent donut hole in the center of the 3 nucleon triangular pattern. Can we simply relate that geometry to the amount of small mass lost when, say, that rare helium-3 isotope is formed? In other words, when 3 separate single nucleons touch and form 3 fused nucleons. Yes, and if nothing else, that geometry will give us a visual memory trick and a feel for the magnitudes involved. First, imagine a single small sphere of the same high nuclear density as the 3 big nucleons around it, but size small enough to barely fit through the small donut hole in this pattern center. Then multiply that small sphere's mass times 2, and that gets twice that much mass. In other words, visualize 2 such small spheres. That is the amount of conventional mass lost when that rare helium-3 fuses together. And that is the amount of mc² energy that is, so to speak, emitted by the fusion. Also, that much emitted energy is termed the so-called binding energy that holds those nucleons together pretty tightly. And our geometric picturesque memory trick has good accuracy with an error of much less than 1%. I realize we're making some simplifications throughout to get this section of the talk done in about a half hour as originally scheduled. I may have an addendum if time permits. Now we'll try to go on to slide 3. Can we further simply relate the just discussed 3 nucleon fusion case and its conventional mass lost to the fusion mass lost when 4 nucleons fuse together, as shown in that top view? In other words, when 4 separate nucleons touch and form 4 fused nucleons. That is thought to be the net effect that powers our sun, the loss of 4 neutral common hydrogen atoms, which produces 1 neutral common helium atom. Yes, things relate. We note that the 4 nucleons shown there form a tetrahedral array, and in a sense it looks like 4 3-nucleon triangular patterns. In other words, 4 triangular planes. And each of those 4 triangular arrays has one donut hole. That is a total of 4 donut holes. We can't see them all very well in the bottom sketch, but the one at the very bottom is quite visible. And that's 4 times as many donut holes as in the previous slide, showing only one single 3-nucleon array. So in a sense, we can expect to quadruple the amount of nuclear fusion energy produced compared to the earlier 3-nucleon case. And that predicts the outcome with an error of about 3.5%. Actually, I'm a little surprised it even came out that close for this reason. We can picture putting inside, say, the cavern space of that 4-sphere tetrahedral, 4 small spheres, each barely fitting through the donut hole, and that leaves barely enough wiggle room for them to wiggle. So analyzing what the ether flow might do inside that empty cavern space is pretty complicated. So maybe nature simplifies things, so to speak, by trying to quantize the amount of mass loss into discrete multiples for simple cases. Next, although we don't show it, next imagine grabbing 3 sets of nucleons, each set consisting of a 4-nucleon array, and bringing them close together, just close enough so they touch in one small triangular region. Thus they would form a beautiful 12-nucleon pattern there, and also with one free extra triangular pattern near where they all touch. That extra free tunnel provides an extra free fusion event without increasing the number of nucleons. Thus, that fancy pattern of 12 nucleons can finally result in a slightly greater average binding energy per nucleon than even the single tetrahedral set of 4 nucleons can provide with regard to binding energy per nucleon. And that net outcome actually occurs when 12 nucleons fuse together to make carbon-12. Similarly, with regard to bringing 4 sets of nucleons, 4 nucleons per set, and the free tetrahedral pattern and extra fusion resulting then, like oxygen 16. All the above is meant to just give you a slight idea for just some of the many combinations and complications possible when contemplating large nuclei. Another complication is that large nuclei contain many, many protons, so that their mutual repelling then becomes great enough to greatly affect the nuclei stability. Thus, for large nuclei, other approaches become more practical than my raw basics donut hole approach. And there exists more practical approaches for those large complicated nuclei, like just applying the beta Y-sector semi-empirical formula. Now we'll try to move on to slide 4. Now, if I get into too much trouble here, I'll go to it. Oh, okay. Well, no, I'm going too high, too fast, I think.
Which one are you going?
Okay.
Got it? Okay,
Well,
click the mouse button.
I'm not quite there.
There you go.
It's really, oh, well, no, believe it or not, you know, maybe one more try here. It's,
Which one do you want to go?
there we go.
Okay,
Is that, okay, well, okay.
got it?
There we see a nucleus with just two nucleons, one proton and one neutron. I can't bring much rationale to the mass loss resulting from that fusion or confusion, but I can say this, that although we note some deep narrowing crevices, there's no nice donut hole that seems to result. And the mass loss is a lot less than for the 3-nucleon case. In fact, the weak 2-nucleon binding energy is like imagining the following amount. Pull a negative electron away from the surface of a positive proton until it's a long distance away. That is roughly the electrostatic energy equivalent involved. Now we'll try to move on to slide 5.
Click.
Well, in this case, I think this will do. Incidentally, the slides the text there will show up, the gist of it will show up better in the proceedings book than this. So don't strain your eyes and just kind of listen. This slide presents a better, more basic method of calculating binding energy of a nucleus. It was pioneered by the prominent textbook writers and scientists, Sears and Zemansky. Unfortunately, it is not used by many scientists today, who sadly exclusively keep using the original, older method. But I use Sears and Zemansky's good binding energy approach and advocate it anyway. They demonstrated it effectively in their book. My raw basics theory tracks closer to reality by using their new method shown than using the old method, but even the old, more common method still shows a close enough correlation between my raw basics approach and reality to be noteworthy. Now let me see if I can get back to that.
Click it again. Click it again. Okay, which one do you want to get to?
I want to just, oh, I see. Well, this is a different, well, okay, let's see if this does it. Okay, one moment. Well, no.
Which one do you want?
I want slide 5, which is this one. Yeah, okay. For some reason, I must have knocked against something. But anyway, to continue with this slide here. Okay, shown here. Now, let me just catch up here a moment. Neutrons are not used in the Susan-Szymanski method because it is more meaningful to start by using the neutral Bohr hydrogen atom as the stable building block to gauge the world. That Bohr atom consists of the mass of an orbiting negative electron plus the more massive positive proton that it orbits. That basic neutral building block also contains the fundamental seed of negative charge, the electron, and positive charge, the proton. But the free neutron is a sort of artificial particle. It is not stable and decays into a proton and an electron, giving off appreciable energy in that decay. That energy had to be injected into the free neutron even to construct it. Shown on the Susan-Szymanski page is how, in effect, the sun starts with 4 neutral Bohr hydrogen atoms and produces, by fusing them, 1 neutral helium atom. That is shown here, the process. And since simple hydrogen and simple helium constitute overwhelmingly most of the mass of the universe, I focused mainly on them. Susan-Szymanski's superior method starts with the basic mass of 4 hydrogen atoms and then subtracts from that the mass of 1 final helium atom made from those. And he does that here. And the mass difference, or conventional mass lost, is the MC squared energy that the fusion produced, and it is considered the binding energy of the helium nucleus produced. But the inferior older method instead starts with the allegedly basic 2 neutron masses plus the mass of 2 hydrogen atoms, and then subtracts from that the mass of the final helium atom produced. The result, when comparing the 2 different methods, seems only slightly different relative to the very huge fusion energy produced, in that case anyway. But in other basic fusion, where fusion events with less energy emitted, serious contradictions and drawbacks arise when the old method is used. Now we'll move on to slide 6.
Click on W.
Well, I think we may.
There you go. Click.
The trouble is,
Yeah,
okay. Let's see.
You want to go to 6?
Yes, which is the last slide.
Right there.
Okay.
Okay.
Again, the more details are shown in the paper. That is, not more details, but more clearly in the proceedings book than here. So we'll just mainly listen. This slide discusses 2 atoms, rare hydrogen-3, having 2 neutrons and 1 proton, and rare helium-3, having 1 neutron and 2 protons. Each atom has 3 nucleons. The upper part of the page shows the old binding energy method applied to each atom. The sad result predicts hydrogen-3 with a much greater binding energy than helium-3, but that is a bad prediction because hydrogen-3 decays and helium-3 is stable. That is, hydrogen-3 decays and helium-3 is stable, exactly the opposite of the old method's implications. But the lower part of the page there shows the newer method applied using only neutral common hydrogen atoms as starting ingredients. Its method predicts that helium-3 has a slightly greater binding energy than hydrogen-3, so we are not surprised that therefore hydrogen-3 really does decay and even produces stable helium-3 as a result. When calculating basic fusion energies, to start with the neutron masses instead of the neutral Bohr atoms is somewhat analogous to starting with the Ptolemaic system instead of the heliocentric system. That ends this main part of my talk, and I think we'll take any comments and questions, and then see if we have time to go on to a more optional supplemental part.
Okay, yeah, okay, well, fire away. Okay, a fascinating approach to look at these donut holes and to see how the donut holes increase in number as the nucleons increase
Yes.
in being attached to each other. I'm wondering whether there might be another way of looking at it. That is that just take one nucleon, assume it has a lot of energy tucked into it. Let's assume that that energy is the energy of vibration. All right? And the vibration runs through it,
Yes.
including its border.
Yes.
Okay. Then it gets fused with a neighboring nucleon. And in that fusion, there is part of each that now becomes shared between the two. And in that sharing process, part of what was in one or the other, where the borders touch, is released because you now have a common border, but it releases, say, that portion of the border of one or the other. And that is also full of energy, vibrating. So in other words, the fusion is releasing some of the energy that each of the two things put together had. I'm not sure if I make that clear, but it's just, perhaps it's an alternate way of looking at how the fusion can release energy. Is that?
Yeah, well, I think that that's a theory or a proposal or approach that is also worthy of course, consideration and you know, like there of course maybe even others. I do want to say one thing that might, if I can get back to slide. Well, let's see, maybe I'll get back to the right one accidentally here. Well, I did, one of the reasons why I went the direction I did, but there are many reasons, but I thought this one was interesting. I started by counting pretending there was glue involved, like, well, kind of like this, that there was glue gluing these things together, and so we would then say for 3 we might have vibrations or glue here, and vibrations and glue there, or vibrations and glue there, and you know that totaled 3. 1, 2, 3. So when you, then I said, well, when you add another nucleon up here, though there are other ways of perhaps of doing it, then you had 1 stick here, 1 sticking here, you had your 3 original sticking points, plus you added 3 more, so that doubled maybe the amount of fusion. I wasn't entirely happy about that because the fusion, when you go from 3 nucleons, the best of the 3 nucleon examples to the best of the 4 nucleon examples, you quadruple the amount of fusion, or the amount of energy released. So because I was dissatisfied with what seems to be simply the doubling of the, well, of the, what I call the glue touching points, because the mere doubling of it wasn't giving me the fourfold or quadrupling of the energy release. So I began to look at the possibility of 4 planes versus 1 plane, or 4 donut holes compared to 1. But in all these visual examples, that has a limited, that's limited in the greatness of the approach, so it doesn't eliminate such considerations as you've proposed with such approaches that you and likely others might also try. Any other comments or questions? Okay, fire away.
Yeah, I have 2 comments. One, when you said there was a loss of energy, what did you mean by that? Is that like a neutrino?
Well, an electron has, I guess I should speak into the mic, an electron has about 0.5 million electron volts. So if we're talking about, say, a number of electrons being demolished, we're talking about a few a few million electron volts, when a few electrons worth of mass are kind of destroyed or given off in the form of energy or whatever. But a major nuclear event, either of these 3 nucleons or 4 nucleons, causes, instead of a few million electron volts, a few million electron volts or whatever, it causes, I'm trying to think of numbers right now, I would say offhand, let's see.
But it causes less? I
No,
mean, is it measured less?
Yeah, the fusion event, I think, would be something like at least 14 million, or you know, who knows, maybe even 27 million electron volts. It would go well beyond simply demolishing 3 or 4 electrons. And I know that things like Wikipedia are somewhat limited and somewhat biased, but they do point out that a nuclear event, in their view, is different than it cannot be well simulated by by an electric event. I say that tongue-in-cheek because I know that there are people who are trying to construct everything using electrical model. But I am kind of a little more sympathetic to this. I mean, to looking for something different than the regular electronic event here.
But Carl, again, I'd like it sometime, maybe afterwards, or take a look at it, maybe email me, because if it's the case that you're looking at this event you're saying, and there's supposed to be extra energy, this smells of stuff, something that comes up all the time. Dr. Carazani has shown that they use neutrinos, which of course, in our opinion, are invented. So it may be the case that there isn't extra energy. They assume there's extra energy and they give it to the magical neutrino, which you can't detect. But let's take that offline, and maybe you could investigate. I'd like to do that, get that information if you could. The second comment I wanted to make, which is really interesting, is with us trying to do this universe hack, hackathon where we're trying to make, come up with mechanical, the mechanical models we are, you're saying that you are using ether, correct?
Yes, I used ether to go under the tunnels to
Right.
cause my, hopefully, Venturi attraction.
Right, so what you're saying is ether's flowing through those and it's causing the pressure difference, and then that's causing the attraction, correct?
That's absolutely correct. And I might say that although I do respect Einstein in many ways, and of course I tend to believe, or at least historically have, that E equals mc squared, although we have heard different opinions on that. I do think that one of Einstein's drawbacks was, at first he said, it doesn't look like there's any ether to me, and it isn't needed in any of my theories, and likely not in physics at all. Then after Lawrence began to kind of get angry at him and so on, and through his own experience, he began to say, well, there is an ether, but it has no mechanical properties. And I don't think he ever got away from that, which I think was a mistake, because I think there's a large amount of physics that becomes pretty apparent as far as possible cause effects if you'll only accept the ether, or something like that. I mean, Dirac had his version. A lot of scientists have had their varying descriptions of something like an ether. Well, anyway, it just, I think that was a misnomer, that we got away entirely from that, and that it seems to me Einstein, so to speak, tried to twist space, or with his curved space, or whatever the common description is, and to try to get away from Euclidean geometry and try to curve up space or whatever. These are stretched things to my conceptual view of things, and I think they're worse than rejecting the ether.
And you're talking about all your diagrams here are showing the nucleus, is that correct?
Yes.
Okay. No, I think there's some, at least from my side, and looking at structures and the ether, how ether sets up structures, how structures are made. It's one of the, what we're trying to do is come up with almost like prototypes of the way ether flow can cause attraction, because in our world there is no such thing as attraction. It's not magic. There's forces somewhere. Why do stars spin in a galaxy and don't go flying off into space? Well, there's not a suction, or even if you think there still has to be something around that to happen. So you're talking specifically about how ether would be working within the nucleus of an atom, correct?
Well, both that, yes, but also a pressurized ether, kind of just about everywhere. Even and especially outside the particles too, because after all, we would not have the Venturi effect that in the case of old carburetors and old cars used to suck in air, due to its low pressure, and that concept used in many old applications in mechanical engineering. That would not work if we didn't have a pressurized air, so that we could have a lower pressure region for that to push into, or try to push into. And similarly, just like we need our pressurized air, atmosphere, and so on, we, in my opinion, need an ether or something like that that is pressurized.
Oh, yeah, I agree.
Yes.
Yes.
Thank you, thank you.
I have two questions. You said the nucleons are positively charged.
Well, two of them are positively charged, and two of them are neutral, say in the case of common helium-4 in the sun.
But then they are brought together by the special nuclear forces.
Yeah, well, yes, that is, I guess, the ongoing accepted paradigm.
Are these forces, are the electrons between the nuclear, are they the ones that's keeping them together? The negative electrons between the nucleons. Are they the forces that keep the nucleon together?
I do not think so, and a kind of major article in Wikipedia kind of discourages a model where charge itself is credited with holding a nucleus firmly together. That does not prove that the charge is not involved. Charge may be involved, and I'll tell you one thing: when you get 80 or 90 protons in the nucleus, or trying to be in a nucleus, not only is charge involved, but that many charges will break up the nuclei, and it does break up as it sends an alpha particle fast away from the scene. I think that whole subject is something I need to think about more, and we should all think about more. I don't have a great convincing model for charge itself to present, as far as all the cause and effect. And as you've brought out in your talk, be certain about shapes, and so on. So again, I guess we'll all be working on that.
Oops, move your mouse.
If two
Just move your mouse.
Oh, what should I do?
Just move it. It'll come back on.
Okay, well
There you go.
If two nuclei combine to make one nucleus,
yes.
then the charge double? Does the mass double or quadruple? Which happen to be?
Well, when two nuclei combine, such as a proton and a neutron, that makes deuterium, which is one nucleus, and maybe the balls are denting each other, maybe they're more than denting each other, but that particular event involving the neutron and the proton has a weak enough binding energy so that charge is a very good